Welcome back. This week in lecture, we'll be covering Chapter 31 on light quanta and Chapter 33 on the atomic nucleus and radioactivity.
In this chapter, we'll cover how quantum theory originated. We'll talk about quantization and Planck's constant, what the photoelectric effect is, how light behaves like a wave and a particle, and then how some experiments such as electron slit experiment and electron diffraction show that light has wave and particle-like properties. And then we'll talk about what the uncertainty principle is. First, we're going to look at how the quantum theory started up. And in 1900, physicist Max Planck hypothesized that when a warm object emits energy, that the energy isn't just lost continuously or in a continuous stream, but it's given off in discrete bundles or lumps, which he called quanta. We now call these bundles of light photons. So for light particularly, we call these bundles photons. And the laws that describe the property of these tiny quanta or photons is called quantum physics. Quantization is the idea that the natural world is granular rather than continuously smooth. So again, that these bundles of light energy are in these packets rather than, in bundles rather than given off continuously. We call that quantization. And quantum physics states that in the micro world of the atom, the amount of energy in any system is quantized, so not all values of energy are possible. And so what this means that, like, if you have a fire that's burning, that it can only burn at certain temperatures, and not every temperature in between. Now, this really doesn't seem logical to us, because we would say that we could measure the campfire and we could get every single temperature in between. But we're only looking down to a certain scale of temperature. So when we're measuring something and, we measure 0.1, 0.2, 0.3 degrees Celsius, these quanta that we're talking about are measured at the level of the photon. And so there's such a small level that if you were to get down to that small level, then the temperature could only be in discrete amounts and not every value in between. And again, that's because you're looking at such a small level, and we don't necessarily see that in our day-to-day lives because we're looking at a much larger scale. Now, the quanta are tiny bundles of light in general electromagnetic radiation. These tiny bundles, again, are called photons. And the energy of each of these quanta or photons is given by the formula that E, or energy, equals h times f, or frequency. And h is what they call Planck's constant. And so again, light's not emitted continuously, but rather is a stream of photons, and each photon is throbbing at frequency f and carrying a total energy of this Planck's constant times f. So the energy of each photon is equal to this certain value h, which is always the same, times the frequency of the light that you're talking about. So what this means is that if you have something with a very low frequency, then the energy is going to equal this set value h times that low frequency, which means that that particular photon will have a very low energy. So for example, microwaves have a low frequency, and therefore the energy of each microwave photon is very low. So when you get hit with microwaves, they're not doing a lot of damage to your body because there's a really low energy per photon. UV light, on the other hand, has a higher frequency, and therefore it's going to have a higher energy per photon and can do more damage to your body. X-rays have even higher frequencies, and they can do even more, they have even more energy per photon and do even more damage. Before we get into the photoelectric effect, let's just real briefly go over these terms just so we're clear on the definition of these. And quantization is the idea that the natural world is granular rather than smoothly continuous. And a quantum is any elemental particle that makes up matter or carries energy. Next, we'll take a look at the photoelectric effect. which shows that when light shines on metal, it's capable of ejecting electrons from certain metal surfaces. And it shows us a model for how matter is radiated off surfaces. And it was hypothesized by Max Planck, again in the early 1900s. So essentially what the photoelectric effect is that when you shine a light down onto metal, the light will eject electrons. And if you have more light, then you'll have more electrons ejected. They're all going to have the same kinetic energy or the same energy. So shining more light doesn't mean that more energy is given off, just that there's more electrons, all with that same energy. So when we look at light, there's been this long-standing debate of whether light is a particle or wave. So all the way back to the time of Plato in the 4th and 5th century, he felt that light behaved more like a wave. And then the Pythagoreans thought that light behaved more like a particle. So there's been this debate on whether light is a wave or a particle. Now, in theory, it should be easy to distinguish because particles move in straight lines unless they're acted upon by a force, and waves can travel through openings and diffract or bend. So as we've seen with like sound, it can go through a doorway and curve around the doorway, so that those waves can bend, and light behaves like both of these. So we'll cover in the next few slides some of the experiments they've done to show how light is a particle, and how light is also a wave. Now, if you were to look at light as a wave, you would expect that low frequency light would eventually build up enough energy to eject electrons. But what we see, however, is that the low frequency light, no matter how long you shine it on the metal, will never eject electrons. Once you get the frequency high enough to eject the electrons, then the electrons are emitted instantaneously, and they're emitted at just the same quickness as if you had a high frequency light. So the high frequency light, the higher the frequency light, you're going to have more electrons ejected. But the second you turn on that light, if the electrons are going to be ejected, they're ejected at the same time with a high frequency light or a low frequency light. And we would expect with a wave that it would take more time for that weaker light source to build up to be strong enough to eject electrons. But again, they eject electrons at the same rate, just more electrons are ejected with the stronger light. So you can see the photoelectric effect when you take a piece of metal and you give it a negative charge. So you have your battery here hooked up to a wire and hooked up to your metal. And so you have a negative charge on this end, and then when you shine the light on there, electrons are given off of that, or ejected from that metal, and they're attracted to the positive end over here. And what we can do is we can see the current flowing through this wire, and we can use that current to calculate the energy of the ejected electrons. So Einstein took all these ideas of what happens when light is shown onto metal and electrons are ejected, and put this all together into the concept of the photoelectric effect. And so what he determined from all this is that light is a stream of particles or bundles of energy called photons, and one photon is completely absorbed by each electron ejected from the metal. So absorption is all or nothing, which is why we see that low intensity light does not, or low frequency light does not eject any electrons, and then higher frequency light can eject electrons. So it's all or nothing, depending on whether the frequency is high enough, and it is immediate. So there's no delay as you would expect there to be if there was a wave energy buildup. So if it was a wave, you'd expect the energy to build up and have somewhat of a delay, and we don't see that delay at all. And then the number of photons in the light beam affects the brightness of the whole beam, and the frequency of the light controls the energy of each individual photon. Okay, so what can we learn from the photoelectric effect? Essentially, it proves conclusively that light has particle properties. Now, keep in mind that we've also seen that light conclusively has wave-like properties, such as we see with diffraction or light bending like a wave. So we'll go into some of the wave-like properties of light here coming up, but just keep in mind with the photoelectric effect, we see that light definitely has particle-like properties. Let's go ahead and do a review question. In the photoelectric effect, the brighter the illuminating light on a photosensitive surface, the greater the, velocity of ejected electrons, number of ejected electrons, both A and B, or none of the above? And the answer is number of ejected electrons. So remember, the speed of the electrons does not change at all, but when you have a brighter light, it just means that you have more electrons. So wave-particle duality just means that waves have that light has properties of both a wave and a particle, as we've been talking about. So a photon behaves as a particle when it's emitted by an atom or absorbed by a photographic film or other detectors. So as we see with the photons bouncing off of a metal surface, it's behaving as a particle, but it behaves as a wave when it's traveling from a source to the place where it's detected. So in this sense, light is both a wave and a particle. So we've seen in the past chapter the double slit experiment, where light passes through two openings, and when that wave essentially hits these openings, we see the wave diffract or bend around those openings. And what we end up with from the interference, where sometimes the waves, the crests meet, and you get a higher crest, and sometimes the crest and the trough cancel out, and you get a low point in the wave. You see this pattern of light, light and dark, and light and dark. And so this is what we would expect to see if light were behaving as a wave. Okay, so what they found is that if you were to dim your light source so that only one photon at a time could get through those double slits, that you'd see those photons start hitting in what sort of appears to be these random places. But then the more photons that hit, so this would be the light for a very short amount of time, the more photons that hit, you start to sort of fill in these patterns. And what we see is eventually the same interference pattern of light and dark that we would expect to see with a wave. So essentially this is showing us that light definitely is a wave. So what we can take away from this is that a photon behaves as a particle when it's being emitted by an atom or absorbed by a photographic film or other detectors. And it behaves as a wave when it's traveling from a source to the place where it's detected. The photon strikes the film as a particle, but travels to its position as a wave that interferes, that has interference. Now, a French scientist named de Broglie in the 1920s asked the question, if a photon of light has both wave and particle properties, then why can't a material particle, one with mass, also have both wave and particle properties? So something like you. And his work on this later earned him a Nobel Prize. And what he found was that every particle of matter is associated with a corresponding wave. So everything, whether it's an electron, an atom, or you, or a planet, has a wavelength related to its momentum, which is given by the formula wavelength is equal to h, Planck's constant, over momentum. So what this means is that if you have something with a very large momentum, so if this number down here is very big, if you think of dividing a small number by a very, very large number, you're going to get a very, very small number. So that would mean that something with a large momentum will have a very small wavelength associated with it. Something with a very, very small momentum will have a very large wavelength associated with it. So for example, something with a large mass and moderate speed has a very high momentum. And what momentum is if something is moving, it's sort of that energy and movement that it has. So if you think of a rock rolling down a hill, a really heavy rock would be hard to stop rolling, and that fact that it's hard to stop moving is because it has a lot of momentum. It wants to keep moving. You think of a very small rock rolling down a hill, you could stop that pretty easy, but a big boulder rolling down a hill, you're not going to stop it because of its high momentum. So things with high momentum, like that big boulder, like yourself, or any other thing really that we can see, is going to have a very small wavelength associated. In fact, a wavelength that's so small that you're not even going to notice it. So you don't see people out there moving around in wave-like patterns. Something much smaller, like an electron, has a much lower momentum. So this number down here is small, which means that you're going to end up with a large wavelength. And so for these objects, things like an electron or a photon or things down at the quantum level, very, very small things, have a much higher wavelength. And so things like diffraction or the wave-like properties are very noticeable. A scientist named Heisenberg determined that since quanta have wave-like properties, when we try to measure them at a particular point, we alter them. And this is because waves cannot be squeezed into a point in space or limited to a single instant in time. So waves move through space and time, and if we try to measure them at one space at one single time, then we are changing them from what they would normally be. There's therefore uncertainty in all measurements, again at the quantum level, because by measuring things at the quantum level, we change things, and this is known as the Heisenberg uncertainty principle. Now, Heisenberg's uncertainty principle only applies to things at the quantum level, or to what they call quantum mechanics, looking at things at the quantum level. It doesn't apply to things at the larger level. So for example, working in a lab, things that we deal with for the most part on a day-to-day level, we can measure with a great deal of certainty because the amount of, by us measuring it, changing things at the quantum level is so minute compared to the measurements that we're doing that we're not altering it enough to really alter our end results. So again, the uncertainty principle just applies to quantum mechanics. That's the end of our week 7 lecture. And just in case you didn't know, we only have 2 weeks of new lecture left. That will be in week 8 and week 9. During week 10, we'll do a review week, and then week 11 will be your final. So we are quickly approaching the end. Great job to everyone. Try to stay motivated in these last few weeks here. The end is in sight. So good job, and keep it up for the last little bit of the course here. If you have any questions as you're going throughout the week, as always, feel free to let me know, and I will be in touch with you again in week 8.
Welcome back to week 8. This week we are going to cover chapter 33 on the atomic nucleus and radioactivity. You'll have your week 8 discussion, and for this discussion and next week's discussion, you're going to be creating an essay question from this chapter. So you'll pick something that you think would be a good essay question from the chapter, and then you will not answer the question. You'll just create the question for your initial post, and then for your reply, you're going to answer one other student's question. And then I will pick one of these questions from week 8 and one from week 9 to put on the final. And then for your week 8 lab, it's an online lab, so you'll go to a site that I provide to you in the week 8 lab link, and you'll do a lab on radioactive dating. So next we are going to cover chapter 33 on the atomic nucleus and radioactivity. This chapter, the topics that we'll cover are X-rays and radioactivity, alpha, beta, and gamma rays, environmental radiation, the atomic nucleus and the strong force, radioactive half-life, radiation detectors, transmutation of elements, and radiometric dating. So far in the course, we've been covering atomic physics, and that's where we're looking at electrons in the atom. And electrons are the things that are located on the outer portion of the atom. They're these negatively charged particles on the outside of the atom. And when you make changes in electrons, these can change things like whether something is magnetic and the charge of something. And this is all under the branch of atomic physics. Now we're going to be looking inside the atom at the nucleus or the center of the atom and changes that occur in this part, the central part of the atom. And this branch of physics is called nuclear physics. So back in 1895, a physicist named William Röntgen discovered something that we later named X-rays. And these were a type of ray that were produced by a beam of electrons striking the glass of a gas discharge tube. And he found that these X-rays could pass through solid materials, they could ionize the air, and they showed no refraction in glass and were undeflected by magnetic fields. First, we're going to talk about X-rays, and X-rays are high-frequency waves. They're electromagnetic, And X-ray photons have a high energy and can penetrate many layers of the atom before they are absorbed or scattered. X-rays do this, for example, when they pass through the soft layer of your tissue to produce an image of the bones inside your body. Within a few months of discovering these type of rays called X-rays, a scientist called Becquerel discovered rays that were similar to X-rays and that are emitted by other elements such as thorium, actinium, polonium, and radium. And the emission of these rays gave us evidence that drastic changes are going on inside the nucleus. So we knew about changes going on due to electrons, which might change the charge of an atom. But these rays being emitted from the atoms let us know that something much more was going on than just changing the charge, so becoming more positive or more negative. And these changes caused by rays being emitted from the atom are due to changes within the nucleus or the core of the atom. And these changes are called, or these rays being emitted are called radioactivity. Radioactivity is a process of nuclear decay or radioactive decay. It's nothing new in the environment. It's been going on forever. And radioactivity helps to warm the Earth's interior. It's in the air we breathe, and it's present in all the rocks, some in trace amounts, but it is a natural process that occurs. So it's not like something that we have just created, and although we certainly can use the process of radioactivity in different ways, which we'll cover, but overall the process of radioactivity is completely natural. Let's look at a question. The radioactive decay of nature's elements does it occur in the soil? We walk on the air we breathe, the interior of the earth, or all of the above? The answer is all of the above. So radioactive decay in elements is occurring everywhere. Radioactive elements give off 3 different types of radiation, and these 3 types are named after the first 3 letters of the Greek alphabet: alpha, beta, and gamma. And alpha rays have a positive charge, and they're basically a stream of helium nuclei being given off. Beta rays have a negative charge. They're a stream of electrons being given off. And gamma rays have no charge. They're a type of electromagnetic radiation, which is a stream of photons being given off. Different substances can stop or block different types of radioactive rays. So for example, alpha rays will be stopped by a piece of paper. Beta rays will go through the paper but will be stopped by a piece of aluminum. And gamma rays will go through the paper and the aluminum but would be stopped by lead. Question here, the origins of radioactivity go back to, so when did radioactivity start? During military activities in the mid-20th century, during the Industrial Revolution 2 centuries ago, the beginning of human era, or before humans emerged on the Earth. And once again, radioactivity has been going on forever, so before humans emerged on the Earth. Any atom that emits an alpha particle or a beta particle, does it become an atom of a different element always? It may become an atom of a different element. It becomes a different isotope of the same element, or it increases its mass. So when an atom gives off an alpha or a beta particle, it will always become an atom of a different element. Food irradiation is a practical use of radiation. It uses gamma rays that are put onto the food to kill the microbes, and it doesn't actually make the food radioactive. So they've tested the food after they've done this process and can tell that there's no radiation actually left in the food. It just kills the microbes. And this is done to food before astronauts go into space so that their food doesn't have certain microorganisms on it that could end up giving them diarrhea and causing problems in space. As we mentioned, radiation's been going on since the beginning of time, and so because of that, radiation is present in the world all around you. So rocks and minerals in our environment contain a significant amount of radioactive isotopes because most of these rocks and minerals contain trace amounts of uranium. Radon is a gas that arises from uranium deposits, and it's a common environmental hazard that tends to accumulate in places like basements after it seeps up through cracks in the floors. You can see this chart down here, the radiation that on average most of us are exposed to every day. So most of the radiation that we're exposed to is natural background radiation. That's about 75% of what we're exposed to from things like cosmic rays, earth minerals, and radon in the air. 15% comes from medicine and diagnostics, 8% from food and water, things such as potassium, 2% from consumer products, and only 0.003% from coal and nuclear power plants and weapons test fallout. So as you can see, most radiation comes from a natural background, and only about 1/5 of the radiation that we are exposed to comes from non-natural sources. Radiation is measured in something called RADS, which stands for radiation absorbed dose, and it's a measure of energy absorbed. 1 rad is equal to 0.01 joules of radiant energy absorbed per kilogram of tissue. A rem, on the other hand, is a measure of the amount of damage done overall. So, for example, an alpha particle with a radiation of 1 rad has a damage amount per that one for each rad to a factor of 10, giving it a health effect of 10 rems. Beta radiation, on the other hand, beta rays, radiation of 10 rads would only have a factor or damage amount of 1 that they do when you're exposed to them. And so they would have a health, so you'd need 10 rads of beta radiation to equal the same health effect or the same number of rems as alpha radiation. So what that's saying is that alpha radiation is much more damaging to our tissue than beta radiation is. Now, it takes about 500 rems of whole body radiation to be considered lethal, which means you have a 50% chance of surviving this dose of radiation if you're given it over a short period of time, such as a day or less. Now, radiation therapy, on the other hand, gives a patient localized radiation, so it's not exposed to your whole body. It's radiation to a certain area, such as a cancerous region, for medical purposes. And they would give you something such as 200 rems each day to a localized area over several weeks to try to kill that specific region, such as the cancer. Here's a chart from your textbook showing the different doses of radiation that you receive from different things around you. So from X-rays, you get a total of 40 MREMs or microrems. Nuclear diagnostic testing is 15. TVs 11. Weapons test fallout 1. Commercial fossil fuel power plants less than 1. And commercial nuclear power plants much, much less than 1. So when your cells are exposed to radiation, there's one of 3 things that can happen. Oftentimes the radiation is not high enough that cells can just heal themselves, and the cells will be completely normal after that. And if the radiation is high enough, some of the cells can be killed. And then the third option is that some cells might survive radiation, but the radiation can cause damage to the DNA. And then any damage to DNA, when DNA gets changed, the DNA is considered mutated. So most mutations don't cause any problems. Other mutations can lead to cells that replicate too often, so they keep dividing and dividing or growing and growing because their stop gene gets turned off. So if the radiation happens to hit in the DNA on the stop gene and that gets turned off, then the cells will keep dividing and growing, and this is what we call cancer. So when the cells just keep, when a certain cell keeps growing and growing, and you get an overgrowth of these mutated cells. So those are the 3 things that can happen if you are exposed to radiation. Now, radioactive tracers is more of a positive use of radiation. So they can take radioactive samples. They've made radioactive samples of all different elements in the lab. And these radioactive elements can be added in small amounts to things like fertilizers and applied to a plant for testing purposes. And they can measure the amount of radioactive fertilizer in the plant with a radiation detector. And so radioactive isotopes that are used, an isotope is just an element that's been changed through radiation. So these radioactive isotopes that are used to trace the pathway of a fertilizer through the plant is called a tracer. And from the measurements of tracing the amount of radiation or radioactive isotopes at different spots in the plant, they can learn how much fertilizer that needs to be used on the plant and where the fertilizer is reaching in the plant, again, for research purposes. So what is a radioactive tracer? Is it a radioactive isotope that's part of the molecule that binds to cancer cells, a small slug of radioactive material that's used to monitor its passage through the human body, a radioactive isotope that is part of an organism whose half-life can be used to date its residence time in the organism, or a radioactive isotope of an element that by itself or in a molecule is used to trace biochemical pathways in plants and organisms. And the answer is D. So it's a radioactive isotope of an element that's been changed and is used to trace the pathways of certain chemicals in plants and other organisms. Next, we'll move on to the atomic nucleus and the strong force. And the strong force is a name for a force that holds nucleons together. And again, nucleons are the protons and neutrons that are located at the center of an atom. And it's a force that exists between particles in the nucleus. Again, these are called nucleons. So we've probably all heard that opposite charges attract and like charges repel each other. So we would expect that since the nucleus is filled with protons which have a positive charge and neutrons which have no charge, that the positively charged protons in the nucleus or in the center of the atom would all repel each other because like charges normally repel each other. But there's this thing called the strong force, or this nuclear force, that actually attracts the particles inside the nucleus and holds them together, but it's only effective over a very, very short distance. So if you were to look at two protons or positively charged particles at the center of an atom, the strong force or the strong nuclear force is very significant, very strong, holding them together when they're very close together. The electrical force, however, is repulsive between these two particles, so it's pretty significantly pushing them apart. And so when you have something significantly pulling it together and pushing it apart, the result is that they stay fairly stable. They are moving around inside the atom, but they're not being shot out of the atom as you would expect if you only had this electrical force or the charge between a positive and a positive. Now, if you were to move those protons further apart, then the strong force or the nuclear force becomes insignificant, as you can see here, because it's not strong enough to hold them together at a distance. The electrical repulsive force is still fairly significant. So if you were to move these protons further apart, they would overall get pushed even further apart because of the electrical repulsive force. But at close distances, they're held together and not pushed apart due to the strong nuclear force or the strong force. So if you remember from the last slide, the strong force is most significant or most effective at holding the particles together when they're close together. And in a small nucleus, so an atom with a small nucleus, the nucleons are closer together, these protons and neutrons, and so the strong force is more significant than it is with a larger atom that has more protons and neutrons in the center of it, and the strong force on the larger atom is not quite as significant. So neutrons and protons, the two particles that are inside the nucleus of the atom or the center of the atom, both have the strong force helping to hold the atom together. And remember that although protons have a significant attractive strong force, they also have a significant repulsive electrical force. And so neutrons act like sort of a cement holding the atom together and overcoming those attractive forces and repulsive forces and keeping the atom together. And the more protons that you have, the more neutrons that you will need to hold the atom together. And most atoms tend to have the same number of neutrons as they do protons for this reason, to help balance out the atom and hold it together. If you remember, an atom with a very large nucleus has a weaker strong force because the protons and neutrons get further apart from each other around the edges of the nucleus or the center of the atom. And so because of this weaker strong force, sometimes a neutron can break off from the center of the atom, and a lone neutron that gets broken off is radioactive and will spontaneously transform into a proton and an electron. And this is how we get alpha decay. So if you remember, there's alpha, beta, and gamma decay. Well, alpha decay is caused by this lone neutron breaking off, and changing the atom from one type of element into another type of element. But again, this only happens for atoms that have a large nucleus. And so alpha decay will only happen in atoms that are very large. So if you're looking at the periodic table and the numbers start from 1 and build up the atomic number, this alpha decay, based on the neutron breaking off, only happens for elements that are higher up on the periodic table. If we take a look here at the periodic table, the number in the upper left-hand corner is known as the atomic number, and that number refers to the number of protons in the nucleus. And as I mentioned, normally the number of protons is equal to the number of neutrons. So as you move up on the periodic table, that means you're adding, as you go from hydrogen to helium, you're adding one more proton. Up to lithium, you're adding another proton. And so the further you go, and the periodic table goes across the rows like this, and then down to the next row. And as you move higher, the atom gets larger and larger. So there's a higher number of protons and neutrons in the center of that nucleus. And once you get to tellurium with atomic number 52, the nucleus of the atom is large enough that the strong force is not quite strong enough to overcome the repulsive force, and you start seeing alpha decay. So anything from tellurium and bigger, so 52 on up, you will see alpha decay. The other two types of decay you can see in any of these atoms, but alpha decay, again, caused by a neutron being given off and breaking into proton and electron, only occur in atoms with an atomic number of 52 or larger. This figure in your text shows you in a picture what's happening with alpha emission. So essentially a neutron, let's say this neutron on the edge here, gets too far away from the rest of the group and essentially becomes a lone neutron. And that neutron will break into a proton and an electron. And that electron or beta particle will be ejected from the atom or ejected from the nucleus of this atom. And then you are left with that extra proton in here. And since there's not enough force to hold that proton in, a group of protons and neutrons will be emitted. And this is your alpha particle right here. Let's do a review question on that. Why doesn't the electric repulsive force of protons in the atomic nucleus cause the protons to fall apart? Is it because the attractive strong nuclear force holds the nucleus together? Electrons passing through the nucleus cancel the proton repulsion? Both of these, or neither of these? The answer is the attractive strong nuclear force holds the nucleus together. Another review question. The strong force is a force in the atom that holds the electrons in orbit? Is it a force in the nucleus that holds the nucleons together? Both of these, or neither of these? And the answer is the strong force is a force in the nucleus that holds the nucleons, which again, nucleons are protons and neutrons, and it holds them together. In the nucleus of an atom, the strong force is a relatively short-range force, long-range force, unstable force, or neutralizing force. And again, it's a short-range force, so it only works at a short distance and works best in smaller atoms. Next, we'll move on to radioactive half-life. The rate of decay for a radioactive isotope is measured in terms of a characteristic time, which we call the half-life. And the half-life is the time for half of an original quantity of the element to decay. So for example, if you had 1 kilogram of an element, such as radium, the half-life is the amount of the number of minutes, days, years that it takes to get half that amount of the atom to decay. So that means you'll be left with going from 1 kilogram to half a kilogram. So essentially half the element will decay within the half-life. So for example, radium-226 has a half-life of 1620 years. So after 1620 years, which is one half-life, half the amount will be left, or half a kilogram, if you started with 1 kilogram. After 3,240 years, which is 2 half-lives, 1/4 of the original amount will be left. And the way that you determine that is you're taking The half, and then you're going to take half of what's left of that, and half of a half is a quarter. If you were to go up another half-life, you'd have half of this 1/4 kilogram left, which half of a quarter is 1/8 of a kilogram. And that will continue on. You'll always have some amount of that element left, because if you keep taking half, 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 it will never go away completely. When an element decays, they don't just disappear, so they're not just decaying into nothing. They are changed into a different element. Uranium-238 will decay into lead-206 through a series of alpha and beta decays. And the half-life of uranium is 4.5 billion years. And so in 4.5 billion years, half of the uranium that we currently have on Earth will be turned into lead. So notice that uranium changes, goes through changes of many different elements. So essentially you're moving through the periodic table, going one atomic number smaller, smaller, smaller as it gives off protons. And as you give off more and more protons, the uranium will be essentially changed from one element to another, to another, to another, until eventually it's changed into lead-206, which is a stable element, and that's why it decays from uranium to lead, because once it hits lead, it becomes stable again. At all these other phases and all these other elements, it's not stable. So a certain isotope has a half-life of 10 years. This means the amount of that isotope remaining at the end of 10 years, will it be 0, 1/4, half, or the same? And the amount is half. So again, within one half-life, you have half the original amount left. An element that undergoes radioactive decay, does it become an entirely different element, either an alpha or beta particle, a less energetic element of the same, or an ion? And it will become an entirely different element. Different things can be, types of detectors can be used to measure radiation, and so as I'm sure you could imagine, there's different reasons why we would want to detect how much radiation is present in certain areas, either for safety and seeing if there's high levels of radiation, or things like the radioactive tracers, and for research purposes. So one type of radiation detector is a Geiger counter that detects incoming radiation by a short pulse of current that's triggered when radiation ionizes a gas in the tube. A scintillation counter indicates incoming radiation by flashes of light produced when charged particles or gamma rays pass through the counter. And so these are just a couple examples of radiation detectors, different ways that we can measure radiation. We've talked a lot about how when elements undergo radioactive decay, they can change into different elements. And they call that when an element undergoes decay and changes into a new element, the term for this is transmutation. And this happens with alpha and beta particles. So when alpha and beta particles are given off, then you get a different element. This occurs naturally, as we've talked about, and it's a natural event that occurs, but it can also be done in a laboratory. So as we talked about, uranium will transmutate into different elements. First would be thorium when an alpha particle is emitted, and this process is continued until it becomes lead, which is stable. We can also make elements undergo transmutations in a lab. This is called artificial transmutation, and this can be done if you were to shoot an alpha particle at an atom, and that would cause the atom to release a proton and transmutate into a different atom. So for example, if you shoot an alpha particle at a nitrogen atom, it will lose one proton and neutron, and it will transmutate into oxygen and hydrogen. Here's a review question. Atoms can transmutate into completely different atoms in nature, laboratories, both A and B, or neither A and B. And the answer is both. So you can have natural transmutation or artificial transmutation. The Earth's atmosphere is constantly being bombarded by cosmic rays, which will cause many atoms in the upper atmosphere to transmutate from one element into another. And this transmutation results in a lot of protons and neutrons being sprayed out into the atmosphere. Most of the protons get stopped somewhere in the upper atmosphere because they interact with other atoms due to their electrical charge. But neutrons have no charge, so they'll often continue down towards Earth into the lower atmosphere. And if one of these neutrons interacts with a nitrogen atom, then the nitrogen atom will capture the neutron and it will become an isotope of carbon. So it will transmutate from nitrogen into carbon, and it will become known as carbon-14. And carbon-14 is a radioactive form of carbon. Most all the rest of the carbon found on Earth is carbon-12, which is not radioactive. So plants will absorb this carbon-14 as they take in air from the atmosphere. They'll absorb some of the carbon, most of the carbon they absorb will be carbon-12, but some of the carbon that they absorb will be this carbon-14, or this radioactive form of carbon. Only about 1/1,000,000th of the carbon in the atmosphere is carbon-14, and the rest is carbon-12. But every living organism will get carbon-14 into their bodies, either if they're a plant by taking it in from the atmosphere, or as an animal by eating other plants, or eating animals who've eaten those plants. And so all living things have a relatively constant amount of carbon-14 in their bodies. Now, when things are living, they are constantly taking in C14, either in the air they breathe or the food they eat. And the carbon-14 will decay because it is radioactive, but then it will be immediately replenished with fresh carbon-14 from the atmosphere of the food they eat. So when you're alive, you're going to be constantly gaining carbon-14 and losing carbon-14, and we'll always have about the same amount of carbon-14 in an organism's body. So when a plant or an organism dies, however, obviously they're not breathing or eating anymore, and so they stop taking in carbon-14 from the atmosphere. And the longer they die, the more this carbon-14 that they do have in their bodies will be lost through decay. So the half-life of carbon-14 is 5,730 years. And what we can do is measure the amount of carbon-14 in an organism and compare it to the amount of carbon-14 in living organisms. And using this half-life of 5,730 years, we can very accurately determine how long ago an organism lived. So if you were to look at the standard amount of carbon in a living organism, and you were to measure the amount of carbon compared to that standard amount, you can see the amount would be, they would have half as much carbon-14 as a living organism after about 5,730 years. Double that time, they'd have a quarter of the amount left, and so on and so forth. And so measuring the amount of carbon-14, or radioactive carbon, allows us again to accurately determine how long ago something was living. Got our last review question here. The half-life of carbon-14 is about 5,730 years, which means that the present amount in your bones will reduce to 0 when you die at about 5,730 years, and about twice 5,730 years, or none of the above. And the answer is none of the above. So the amount of carbon-14 will never reach 0, because again, if you're always taking half of some number, you'll never get down to 0. So you can get a very, 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 very small amount, but never 0. And that's the end of our week 8 lecture. Just want to say great job to everyone keeping up with assignments. You've all done a great job every week on getting your homework done and your labs done and discussions. And I know it's a lot of work and takes a lot of motivation to keep up with that throughout the whole term. So great job. We're getting very close to the end, so keep it up just a little bit longer. And let me know if you have any questions throughout the week.